Hey everybody, I'm Suhana Singh, and today is day 6 of learning machine learning in the simplest way possible. So, in day 6, we will do the basic concepts in machine learning. First, let's look at features and labels. Features are basically inputs. In machine learning, features are the pieces of information or data that we give to the machine so that it can learn and make decisions. You can think of features as the inputs or the clues the model uses to understand a situation. Each feature represents a different detail about an object or event they're trying to study. For example, if we're building a model to predict whether a fruit is an apple or an orange, the feature might include the fruit color, weight, and texture. In a data set, these features are usually organized in columns, and each column showing one type of detail, like color, and each row being one example, like one fruit. The more meaningful features you give to your model, the better it can learn. However, not all features are equally useful. Some might be noisy, irrelevant, or even confusing. So part of the machine learning process is choosing and preparing the best features. And labels, basically the outputs. Labels are the answers or results that we want the machine to learn how to predict. In simple terms, the label is what we're teaching the machine model to find. It's like the correct answer we already know for each example in our training data. So, if you have a photo of a cat and you're training a model to recognize animals, the label would be cat. If you're predicting house prices, the label would be the actual price of each house in the dataset. During training, the model looks at the features like size, location, number of rooms, and the label, that is the price, and tries to learn the patterns between them. Then once it has learned enough, you can give it just the features of a new example, and it will try to guess the label on its own. Without labels, the model wouldn't know what it's supposed to predict. That's why they're such a key part of supervised learning. Number 2, training, testing, and validation. Training is a process where a machine learning model learns from data. This is like the classroom phase where the model studies many examples to understand how inputs, that's the features, are related to outputs, the labels. For example, imagine you're building a model to recognize handwritten digits from 0 to 9. During training, the model looks at thousands of images of digits, each labeled with the correct number they represent. It learns to recognize patterns like how a 3 usually has two curves, or how a 7 often has a straight line with a short dash. The goal of training is for the model to figure out the best internal rules or equations that can turn inputs into accurate predictions. Just like a student needs a lot of practice questions to learn, a model needs a lot of training data to learn well. The more examples it sees, the better its chances of learning correctly, as long as the examples are good and diverse. Now, testing. Testing comes after training and is like the final exam for the model. In this step, we check how the model performs on brand new data that it has never seen before. This is important because we want to know if the model has really learned or if it just memorized the training examples. For example, after training the digit recognizer, we give it new images of handwritten numbers that weren't part of the training set. If the model can still correctly predict these new digits, it means it has truly learned to recognize numbers. But if it fails, it's a sign that it hasn't generalized well. The testing phase helps us judge how useful the models will be in the real world, where it can always face new and unseen data. Think of testing as giving your trained student a surprise test to check what they really know. Validation. Validation is like a practice test during training. used to check the model's progress and help improve it better before the final test. When we train a model, we often need to make choices like how many times should the model go over the training data, or what size should the learning steps be? Should we add any technical to avoid overfitting? To answer these, we have a validation set, which is a separate group of examples not used for learning, but only for checking. For instance, while training the digit recognizer, we might stop after every few rounds and test it on the validation data. If the performance improves, we keep going. But if it starts to get worse, we may be overfitting and it's time to stop or adjust the settings. The validation steps help us tune the model and make better choices without touching the test set until the very end. It acts like a trusted guide during training. 3. Overfitting versus underfitting. Overfitting happens when a machine learning model learns the training data too well. So well that it memorizes every little detail, including noise and random patterns that don't matter. While this might sound like a good thing at first, it actually is a problem. A model that overfits performs very well on the training data but struggles when it sees new unseed data. It can't generalize because it's too focused on what it has already seen. For example, imagine teaching a student math by giving them only one set of practice problems. If the student memorizes the exact answers to those problems, instead of learning how to solve them, they'll fail when they're given a slightly different problem. That's overfitting. In machine learning, this often happens when the model is too complex, like a deep neural network trained on a small dataset, or when training goes on for too long. So to avoid overfitting, we can simplify the model, stop training at the right time, or use techniques like regularization and dropout. So in simple words, overfitting means too much learning, and it's great on training but bad on new data. Now, underfitting is just the opposite problem. It happens when the model is too simple or not trained well enough to capture the real patterns in the data. An underfit model performs poorly on both the training data and the test data. It's like a new student who didn't study enough or didn't understand the basic concepts, so they can't even answer the practice questions correctly. For example, if you use a very basic model, like a straight line, to predict something complex like housing prices, which may depend on many other things like location, size, or number of rooms, your model may not be able to catch up with the real trends. This results in predictions that are way off. So underfitting usually happens when the model is too simple for the task, or if we don't train it long enough, or if the features are poorly chosen or too few. To fix underfitting, we can use a more powerful model, train it longer, or give it better and more informative features. In simple words, underfitting is equal to too little learning, which get bad on both training and new data. 4. We have accuracy, precision, recall, and F1 score. So accuracy is the simplest and most commonly used evaluation metric. It tells us how often the model was correct overall. To calculate it, we divide the number of correct predictions by the total number of predictions. For example, if your model predicted 90 out of 100 emails correctly, as either spam or not spam, the accuracy is 90%. It's like saying, how often did the model get it right? However, accuracy can be misleading, especially if the data is imbalanced. For example, if only 5 out of 100 emails are spam and the model predicts all emails as not spam, it would still be 95% accurate. But it's actually doing a terrible job at detecting spam. That's where the other metrics like precision and recall become important. Now, precision tells us how many of the items the model marked as positive, example spam, where it's actually correct. It's like asking when the model says something is positive, but how often is it right? For example, if the model says 10 emails are spam but only 7 of them really are, then the precision is 7 by 10 or 70%. So precision is especially important when the cost of a false positive is high. For example, if you're predicting cancer and you don't want to wrongly tell healthy people that they're sick, you want to make sure that when you say positive, you're really confident about it. Recall, also called sensitivity. It measures how many of the actual positive cases the model managed to catch, and it answers the question, out of all the real positives, how many did we find? For example, if there are 10 spam emails and the model correctly identifies 8 of them, the recall is 80% or 8 by 10. The recall is important when missing a positive case is dangerous. Think of a fire alarm. You'd rather it go off even if there's just smoke rather than miss a real fire. So in medical diagnosis or fraud detection, high recall is often more important than precision. And F1 score. F1 score is balance between precision and recall. It gives a single number that tells you how well your model is doing when both false positives and false negatives matter. It's it's especially helpful when your data is imbalanced and you want a more fair measure. So the F1 score is the harmonic mean of precision and recall, which means it will only be high if both precision and recall are high. If one of them is low, the F1 score will also be low. For example, if your model has 90% precision and 90% recall, the F1 score is about 90%. But if the precision is 90% and recall only 50%, then the F1 score drops to around 64%. This helps keep the model honest and balanced. Now we have bias variance trade-off. So bias variance trade-off is a key idea in machine learning that explains the balance between the two types of errors a model can make, bias and variance. To build a good model, we need to find the sweet spot where both are balanced. Too much of either one can hurt performance. Now, bias is basically underfitting. It refers to how much error is introduced by simplifying the problem too much. A model with high bias makes strong assumptions and doesn't learn enough from the data. It's like a student who assumes every math problem can be solved in one way even if it's not true. For example, using a straight line, the linear model, to predict something complex like house prices, which may depend on many factors, might lead to poor predictions. So this is underfitting, where the model is too simple to capture the real patterns in the data. So high bias is equal to model is too dumb or rigid, which is equal to poor predictions on both training and test data. Now variance is like overfitting. It's the error that comes out from a model being too sensitive to the training data. A model with high variance learns too much. It even learns noise and random details in the training data that don't generalize well to new data. Imagine a student who memorizes the exact answers to practice questions but doesn't understand the concept. They fail when the question changes slightly. That's overfitting. A high variance model might do extremely well on the training set, but perform poorly on the test set because it hasn't learned the general rules, just the training examples. The trade-off. The challenge in machine learning is to find the right balance. A model with too much bias is too simple and misses the point. A model with too much variance is just too complex and gets confused by random noise. The bias-variance trade-off means that you make a model more complex to reduce bias. Its variance might increase and vice versa. Now the goal is to choose a model that's complex enough to learn the important patterns, but not so complex that it starts memorizing things it shouldn't. Conclusion. In this lesson, we covered the key building blocks of machine learning. You learn what the features and labels are and how models using training, validation, and testing data. We also explored the common challenges of overfitting and underfitting and how the bias variance trade-off helps us balance simplicity and complexity. Finally, we discussed important like evaluation metrics like accuracy, precision, recall, and the F1 score, all crucial for judging how well a model performs. Together, these concepts form the foundation of machine learning. With them, you're now even better equipped to understand, build, and evaluate machine learning models more confidently. Thank you.